Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're looking at how you solve first-order differential equations by using an integrating factor. But before we do that, some differential equations can be solved just by making use of the product rule for differentiation and implicit differentiation. For example, if you had to find the general solution to the differential equation x to the 4 dy by dx plus 4x cubed y equals cos x, these two terms here on the left-hand side can be combined together into one differential, d by dx of some function of x and y. And on the right-hand side, we don't actually do anything. We just leave cos x as it is. Once we've done that, it's then possible to integrate both sides of the equation with respect to x. Now, how do we combine these two terms into one differential? Well, d by dx of x to the 4y will give us both of those terms. If we wrote down the x to the 4 and differentiated y, we get x to the 4 dy by dx, and we're using the product rule here. If we then wrote down the y and differentiated x to the 4, we get 4x cubed times by y. So differentiating this does give us both of those terms, and we've done nothing with the right-hand side so far. Having written it like that, it's then possible to integrate both sides of the equation with respect to x. So integrating the left-hand side with respect to x just gives us x to the 4y. Integrating cos x gives us sin x, and we do need to remember to add on the arbitrary constant in these questions. We've been asked to find the general solution. Now, the general solution is where you find y as a function of x. So we do need to divide through by x to the 4, and then that will give us the general solution. Y equals 1 over x to the 4 times sin x plus c divided by x to the 4. Now, in that example, it does feel that we were just a little bit lucky in being able to convert the left-hand side of the equation into a single function that we could integrate. But it turns out that we can always multiply first-order differential equations of a certain type by an integrating factor. And it makes what we did on that last question always be possible. Now, if we've got a first-order differential equation of the form dy by dx plus py equals q, where both p and q are functions of x, then an equation like this can be solved by multiplying both sides of the equation by an integrating factor, often abbreviated to if, which is equal to e to the integral of whatever p is, that function, with respect to x. Now, when we do that, and when we multiply through by that integrating factor, we get e to the integral of p times by dy by dx plus py times by e to the integral of p equals q times e to the integral of p. And these two terms here can then be combined together just like we did in that first example. And you get d by dx of y e to the integral of p. And the right-hand side we haven't done anything with yet. Then you integrate both sides with respect to x. And when you do that, the left-hand side just becomes y e to the integral of p. And this whole right-hand side does need to be integrated. Sometimes that's straightforwards. Quite often we have to use integration by parts. The left-hand side is just y times by the integrating factor that we worked out initially. And as I said, the right-hand side, you will need to integrate that using standard techniques. So that's the theory. Let's have a look at an example. So I've summarized the key things you need to know there and how you find the integrating factor. And we're given the differential equation. DE is a frequent abbreviation for differential equation. dy by dx minus y over x is equal to x squared. And we're asked, first of all, to find the integrating factor for that equation, then to find the general solution, and then to find a particular solution if we're told that y of 1 is equal to 0. Now, I'll let you have a go at this yourself first. So try and work your way through it. Pause the video and then come back to me again when you're ready. Okay, let's have a look at how all of this works out in practice. So the first thing we have to do is find the integrating factor that we're going to multiply through by. Well, the integrating factor is e to the integral of p dx. Well, in this equation, be careful here. P is equal to minus 1 over x. P is just a function of x. Remember, you've got p times by y. So we've got minus 1 over x times by y. But p is just the function of x, minus 1 over x. Q is more straightforward. Q is just the function on the right-hand side, x squared. Now, the integrating factor is e to the integral of this function, p. So that's e to the integral of minus 1 over x. Now, at this point, we need to integrate minus 1 over x. If we integrate minus 1 over x, we'll get minus log x. This next step isn't obvious, but we've got e and log. We can very nearly cancel these out, but we need to deal with this minus first. Using the law with powers, that's the same thing as e to the power of log x to the power of minus 1. Now, having done that, e and ln are inverse functions, so they just cancel each other out. And all we're left with is x to the minus 1, which is 1 over x. So that's the integrating factor, 1 over x. The next thing is to use that integrating factor to work out the general solution. The way we use it is we multiply through every term by 1 over x. So 1 over x times by dy dx minus 1 over x times y over x equals 1 over x times x squared. And tidying that up gives us 1 over x dy by dx minus y over x squared is equal to x. And the reason why we do that is because these two terms can now be combined into one differential. So you can combine these together as d by dx of y over x. And if we were to differentiate that, first of all, you'd write down the y and differentiate 1 over x. That would give you the minus y over x squared. Then you'd write down the 1 over x and differentiate the y. And that would give you this term here. Once you've done that, you then integrate both sides with respect to x. Integrating the left-hand side just gives you y over x. Integrating x gives us a half x squared, and we do need the arbitrary constant. Now, the general solution should just have y on its own as a function of x. So this x will need to multiply through by, and that gives us the general solution, y equals a half x cubed plus c times by x. Part 3 asks us to find the particular solution of the differential equation, given that y of 1 equals 0. Now, the notation here you may not have seen before. Y of 1 equals 0 means the same thing as y equals 0 when x equals 1. So that would be the x value. Y of 1 means what is y when x equals 1? The answer to that is 0. Now, you may see that notation either in the textbook or possibly on the exam. The general solution we found just now, y equals a half x cubed plus cx. If they give you some sort of initial condition like they've done here, all you have to do is substitute that into the general solution to find c. Once you've found c, then you've got the particular solution. So substituting y equals 0 and x equals 1 into the general solution will give us this. That simplifies to 0 equals a half plus c, which means that c must equal minus a half. So the particular solution is y equals half x cubed minus a half x, putting c equals minus a half in there. Okay, example 2. It's very similar. Given the differential equation cos x times dy by dx plus sin x times y equals 1, as before, we're going to have to find the integrating factor first, then find the general solution, then find the particular solution given that y of 0 equals 1. But before you get started, do just be a little bit careful. As we said, this method works as long as the equation is written in this form. So dy by dx on its own plus some function of x times y equals some other function of x. So this cos x we're going to have to deal with before we get started by dividing through by it. Anyway, I'll let you have a go, pause the video, see how it goes, and then come back to me again when you're ready. Okay, let's have a look at this question. So to find the general solution, we're going to have to find the integrating factor. But before we can do anything, we do need to deal with the form of the equation, and we need to write it in the standard form. That means we need to divide through by cos x. Dividing this by cos x will just give us 1, which is what we want. Sin x over cos x is tan x, and 1 over cos x is sec x. Now it's written in the standard form, and we can just use the normal method. So p is this function here in front of the y. P will equal tan x. The integrating factor is e to the integral of p, so that's e to the integral of tan x. Now this is a standard integral. It's not one you're expected to know off by heart, but you would need to be able to look it up in a formula booklet. The integral of tan x is the log of sec x. So integrating tan x gives us that. Then the e and the log, because they're inverse functions, they just cancel each other out, and the integrating factor is equal to sec x. Once we found the integrating factor, we can then multiply through by it. So multiplying each of these three terms by sec x, we get sec x times dy by dx, plus sec x tan x times by y, and then sec x times sec x is sec squared x. The reason why we do that is because these two terms can then be combined together in one single differential. In this case, it's the differential of y times by sec x. If I write down the sec x and differentiate y, I get the first term. Write down y and differentiate sec x. The differential of sec is sec times tan, so I would get that term. Now we can integrate both sides with respect to x. Integrating the left-hand side gives us y times sec x. The integral of sec squared is tan, and don't forget the arbitrary constant. To get the general solution, we need y on its own, so we're going to have to sort this out. Now, I think the easiest way to do that is to write sec is 1 over cos, tan is sine over cos, and then multiply through by the cos x. Multiplying through by cos x gives us y equals sine x plus c times by cos x. We're asked to find the particular solution of the differential equation, given that y of 0 equals 1. Now, just remind you, that means x equals 0 there, and when x equals 0, y is equal to 1. So y of 0 equals 1 means exactly that. The general solution is y equals sine x plus c cos x. All we have to do is substitute these two values of y and x in order to find the arbitrary constant c. And that gives us 1 equals the sine of 0 plus c times by the cosine of 0. The sine of 0 is 0, the cosine of 0 is 1, so that gives us c equals 1, which means that the particular solution is y equals sine x plus 1 times cos x plus cos x. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 97 and have a go at exercise 5b. Thank you very much for listening, and cheerio.